Again, this is our Winter Weather 202 presentation. I'm Joe Deli Carpini, the Science and Operations Officer. And joining me are a couple of familiar faces to those of you who have attended our webinars. Bryce Williams, one of our meteorologists and manages our social media program, and Rodney Chai, one of our meteorologists, who I think Bryce is becoming one of our up-and-coming winter weather forecasting stars. He's been involved,
no doubt.
involved in a lot of our storms so far this year. So Bryce and Rodney, both welcome, and thank you for helping out as always.
Looking forward to it.
Okay, so I'm going to get started, and then I'll hand it off to Bryce and Rodney. So in Winter Weather 202, we're going to be looking at forecasting tools. So that comes really into three different categories. One being observations, which many of you are probably familiar with, surface observations from weather stations, upper air observations from from balloons, and we'll talk a little bit about that. Then satellite, and then radar as well. Also talk a little bit about model forecasts and kind of things to look for, some kind of rules of thumb that we use when we forecast winter storms and kind of our approach to forecasting winter storms. We know a lot of you probably look at the model data online, and we're kind of blessed with having models available pretty much freely now, and you can look out to 10 days or so into the future. But a few cautions you want to take when looking at some of the data, so we'll go through that. That includes our global models, which talking about things like the European model and the GFS that you may be familiar with, and some of the high resolution models and ensembles too, and something called teleconnections, which I'll get into here first, kind of a way of looking at the overall maybe global pattern or pattern over North America to kind of put you in the ballpark as to maybe where a storm will track and some of the effects it will produce. So to start, we're going to talk about the jet stream, and this is really what drives our winter storms. In the wintertime, the jet stream is stronger than it is in the summer because we have greater temperature contrasts from north to south. So think from the poles down to the equator. Now, in the lower left here, you can see some what are called ridges and troughs. So ridges are kind of wobbles and waves in the atmosphere. So the ridges are areas of warmer weather that I'm pointing to here. A trough is kind of a dip in the jet stream or the upper flow where you have typically colder weather. So again, these areas of lower pressure that are associated with colder air are called troughs, and higher pressure and relatively warmer air are known as ridges. So those really are kind of what drives the weather patterns, and depending on how the jet stream is set up for a particular event, kind of determines where a storm will track. So when we talk about teleconnections, the best example I can think about is maybe you and a friend have a jump rope and you're flipping it up and down, and you see these waves kind of forming on the jump rope. You'll have, if there's a ridge or a area where the jump rope goes up in one area, there's a dip in another, which is known as a trough. So we can do the same thing with the jet stream. And there's two indices we kind of look at in the wintertime. One is called the NAO, which is the North Atlantic Oscillation rather. And that's when we have our blocking near Greenland, and we'll show a little example of that in a minute. But when we have that pattern in a negative NAO, that's blocking that allows storms to slow down over our area as they move up the coast. And often we have enough cold air to produce a fairly sizable snowstorm. Now, another pattern we look at is called the Pacific North American pattern, or PNA. And that's a pattern of a ridge in the western U.S. and a trough in the eastern U.S. So obviously we want a trough here in the east to help drive the storm up the coast, bring in some Atlantic or sometimes even tropical moisture. But we want that ridge out west, because what that ridge does is the stronger it is, and it's typically over the northern Rockies, that will make the trough even deeper or more along the entire stretch of the East Coast, which is favorable for winter storms. So the combination of these two doesn't always guarantee we're going to have a winter storm, but it's kind of putting you in the ballpark or in the neighborhood to be under favorable conditions for some decent winter storms. And of course, the phone rings as I'm talking. So let's talk a little bit about the NAO here. This is during a positive NAO, which is a little less favorable for a big snowstorm in our area. And if you look at the the left image here, you'll notice, here's Greenland, first of all. And you'll notice we've got a kind of a trough over Greenland, and that's kind of unfavorable. And what the NAO really is, it's the difference in pressure between Greenland and the Azores, which are located out here. So When you have a positive NAO, the pressure here is lower than it is over the Azores. And what happens is mild air tends to flood in. Usually we're under some sort of Pacific air. And any storms, if they do form, they tend to go inside toward the Great Lakes. So those are warmer storms for us. In addition, we see these above average heights over the western Atlantic. And think of that as our subtropical high. So the Bermuda High during the summertime, while most of the time in the winter, it's centered out over the Azores in the Atlantic. But occasionally, it makes its way toward the East Coast. And that's when we get our milder stretches of weather in the winter. So obviously, this pattern is pretty unfavorable for significant snows here in the East. And you can see the surface temperatures here, the difference, the anomalies. It's all above average here in the East. Now, the other side of the coin, which is more favorable for us, is when we're in a negative NAO. And this is when you have kind of the reverse. You have higher than average, what are called heights, or a high pressure system over over Greenland, and lower pressure out over the Azores. So what you have is this high pressure block, and it brings in much colder air into the region. It forces the storms coming up the coast to move more offshore or parallel to the coast. So this is when we tend to get our more significant winter storms in this regime. And this is kind of in the pattern we've been in the past few weeks, where we get these storms moving up the coast, and at least the potential, if all things time right with the cold air, to get some snow. But typically the negative NAO is much colder than average temperatures here in the eastern U.S. So again, doesn't guarantee we're going to get a winter storm, but it puts you in the ballpark that if you get a low to develop, odds favoring better chances of snow. Now, the other thing is you see transitions occurring over weeks at a time. So the NAO is typically predictable over about a 2-week period. So that's, to me, how we can best predict our winter weather. We can't go with these 3-month outlooks necessarily. It's over a few weeks at a time. And during these transitions from negative to positive and positive to negative, that's also a time when we can see our biggest winter storms. So that's also a thing to watch. And we'll include the link at the end so you can monitor what the NAO is doing. But when you see transitions or when it's highly negative, that's when we're favored for a good winter storm. And as this slide mentioned, also the placement of it matters. Where these height anomalies are, we really want to see them over Greenland. For having the blocking up there, so as the storms move up, they really can't go anywhere. They can't escape inland, and typically they don't head out to sea, but occasionally they can. And you can find the forecasts of NAO and PNA from the Climate Prediction Center at cpc.ncep.noaa.gov. Forecasts are available to about, I believe, out to about 10 to 14 days, but that's something you can take a look at from home. So now let's move on to why, is there such a variety in our winters? And it all has to do with storm track. So storm track is largely driven by what I just mentioned, by these larger circulations, the NAO and the PNA. But you can see we have all different types of winter storms. Storms that track west to east, these are kind of the Alberta clippers that bring flurries or a little light snow and usually bring Arctic air behind them. And then we have our more coastal storms. Obviously, the good ones move up the coast here, but sometimes we have our inland, we call inland runners, that we're on the mild side of those. They tend to be snow to rain or just rain entirely, much like we saw Christmas Eve into Christmas Day. So the one thing we always want to refer to here is the 40-70 benchmark. That's latitude of 40 degrees north, 70 degrees west. We refer to that in our forecast discussions all the time, so I'm sure many of you are familiar with that. But why is that important? Well, that really sets the stage for where the heavy snow is going to be. So if we start first with an offshore track, and this is what we call a storm outside the benchmark. The low is fairly far offshore. At best, the heavy snow will graze the south coast, Cape Cod, and the islands, but sometimes it can even be displaced further offshore and we get a total miss. Typically lighter snows back across much of southern New England, but again, if the low is farther offshore, we might get shut out completely, which I believe is the case this weekend and early next week. We have a couple of lows that are expected to track well south of our region. Now, if we bring the storm over the benchmark, that's that 40-70 crosshair you see there. This is a classic setup for heavy snow here in southern New England, particularly from Hartford to Providence to Boston in the highly populated corridor. Typically what will happen is we'll get snow or snow to rain on the Cape and the islands because typically milder air is drawn in, and lighter snows are pushed further north across parts of northern Massachusetts and into central New England. Occasionally, though, we can get a second band of heavier snow further to the west, and that's what happened with the December 16th to 17th storm. But typically when you see a storm over the benchmark, think heavy snow, Boston, Providence, and Hartford. And finally, a storm that goes inside the benchmark, that's a storm that tracks maybe on the south coast or into Rhode Island and southeast Massachusetts, or even maybe as far as Worcester. That's going to be rain for much of the area. Sometimes it'll start as snow if it's cold enough, but we'll transition to rain typically. Heavy snow is displaced further to the northwest across central or even northern New England and much of upstate New York, and lighter snows to the north of that. So those are really the three scenarios that we look at when a storm is kind of in the offing several days out. Where is it going to be in relation to that 40-70 benchmark? So let's talk a little bit about the weather models. What are they? Well, they're really just a series of mathematical equations. That's all they are. And they do billions of calculations in a matter of seconds. So what they require are some initial conditions, and that means observations, both from weather stations, satellite, upper air balloons. And all of these equations are simulations of the atmosphere. Think things like physics for the most part. And they provide graphical output in various forms like you see online. Now, the global models that cover larger sections of the Earth, that's why they're called global, they typically run 4 times a day. But all of the different models have different resolutions, meaning they cover different areas. We have the global models that cover maybe the northern hemisphere or southern hemisphere. Then we have what are called the mesoscale models, which cover maybe a region like the Northeast, and high resolution models which maybe cover even smaller area like a state. They all have different initial conditions, how they incorporate all that observed data. Things like parameterizations, how do they handle things like convection, developing thunderstorms, things like that. How do they handle melting of precipitation? And all different schemes. That's why we have a bunch of different models. Each model does not work the same way for a reason. We don't want to get the same answer. So, for example, the European model has different parameterizations than the GFS model, and that has different parameterizations and schemes than the NAM model. So we'll talk a little bit about, show some of these models, but that's why we have all different models, and one is not necessarily good over the, better over the other. Each has its strength for a particular situation. So let's talk about a couple of the global models, as I mentioned. The GFS is the United States model. The ECMWF is known as the European model. You can see these go out a number of days, 10 to 16 days. And people kind of wonder, why is that? Well, these models, these global models, actually give input to climate models. So it's important for the climate model, which goes into things like weeks and months or even years, to have that input out to about 10 to 16 days to kind of get it started on the right track. You can see the different resolution. We use metric, so the GFS is 13 kilometers in the horizontal. The European model is 9 and 16 kilometers. I believe it's down to 9 kilometers now. And what that means is the higher resolution is able to resolve more localized weather features. But these models are really designed for large-scale weather systems. So think things like winter storms and even tropical systems, things that cover large expanses of either America or Europe. They don't do as well with smaller scale features such as thunderstorms or maybe the small scale heavy snow bands in a winter storm. A couple of other global models you're probably familiar with. Canada has its own. Goes out to 10 days, and the UK Met model, which goes out to about 6 days. These run at about the similar resolutions, 15 kilometers for the Canadian and 10 kilometers for the UK. And these are also just other models to check, for winter storms as well. They run different assumptions, different equations than what the GFS and the European model use. So those are the 4 main global models that we look at. So just our usual caution, you've probably seen this on social media. So how accurate is that model forecast beyond 3 days? Well, not really necessarily too accurate. Errors with a model actually increase exponentially with time. So errors in a 24-hour forecast compared with, say, a 72-hour forecast is a significant difference. You can see here an average model error at 3 days is over 150 miles. So a low pressure system you might see in 3 days out that looks great right over the benchmark. Well, it's probably not going to end up there. Typically, it'll end up either a little inside toward the coast or maybe a little bit farther offshore. So we typically don't want to lock in with these models really beyond a couple of days, and that's why we tend to look more at ensembles, which we'll talk a little bit more about here. So speaking of ensembles, these are known as kind of groups of individual models. So think of it this way: the GFS ensemble is actually made up of 21 different runs of the GFS, the same model. The difference is we tweak things on each of those 21 models. So model run number 1 will have different maybe initialization than model 2, 3, 4, 5, etc., or a different physics package. They're all a little bit different. And what that does is it helps iron out the uncertainty in the forecast. So instead of one solution, like the GFS from 12Z, like we like to say, you have a range of solutions of that same model, which helps us iron out things like uncertainty with position of a low or amount of rainfall or amount of snowfall. And the output, there's a few ways we can see the output. You've probably, if you're more familiar, you've seen it online, different things like low placement or low tracks. This is an example of tropical, or what are called plumes. And this is output of precipitation for a particular event. You can see each different member has a different answer, kind of how much rain is going to fall, anywhere from maybe a ½ inch to 2.5 inches. So I will get more into this in our review of the Christmas Eve, Christmas Day storm, because it's a good example of how to use these what are called ensemble plumes. And finally, the situational awareness table is another thing that we can use for ensembles. These are used at longer time ranges, typically 3 to 5 days out. So we tend to start with these, but they can help us with awareness of a potentially significant event. And they're compared with climatology. So it's what the model is forecasting compared with what should be expected for the region. So it doesn't tell you the exact answer, where the high wind's going to be, where the heavy rain's going to be, but it tells you somewhere in that region, and in this case, this is a table of the Northeast, there could be a significant event. So you can click on some of these, and we'll give the link at the end, but really the things we key on are WSP, which is wind speed, Q and PW, which are kind of moisture. So think wind anomalies and moisture anomalies. And the greater these numbers are, the more anomalous or unusual an event can be. It's not a guarantee an event will occur, but again, like having that negative NAO, positive PNA, it's putting you in the ballpark for a potentially significant event. So with that, I believe I'm handing it off to Bryce, who will talk a little bit about the mesoscale and high-res models, unless I'm incorrect. Is it
Yes.
Bryce? Yeah. Okay, go ahead, Bryce.
You're correct. Thank you, Joe. All right, so Joe talked about global models, and so I'm going to move into smaller scale, we're going to start with what's known as the North American model. This is our main, what's known as the mesoscale model, and this covers, obviously, North America. So we basically, the two that we use are the regular NAM and the downscaled 3 kilometer NAM. And so these that basically just has to do with their horizontal resolution. Now you can see that the regular NAM has a 12 kilometer horizontal resolution and 60 vertical levels, whereas the 3 kilometer NAM has a 3 kilometer horizontal resolution and a few more vertical levels. Both of these are American models run at NOAA and INCEP. And so you can, there's all sorts of parameters just like the global models, but these basically come into play when we're about 2 to 3 days out. They don't go out as far, you see only 2.5 to 3.5 days, but they have higher resolution. And these are when we really start to get in winter weather, when we start to get into the time range that we can really start to hone in on what we think is actually going to happen. So once we get past that, we get into even smaller time scales and horizontal resolution. And these are called convection allowing models. Basically, this just means that the model itself is able to have such a small scale or a small resolution, a good resolution, that it can resolve even the smallest features of convection, or really what we call thunderstorms. So it can model simulated reflectivity, which is just basically a simulated radar, to really get details on, say, squall lines or supercells, that kind of thing. So it can get down to the nitty-gritty of a storm, and including winter storms. And so these forecast very minimal with time. We're looking at 18 to 36 hours, but the resolution is down to 3 kilometers or even less in some cases. That the HER is the high resolution rapid refresh model. We call it the HER, and this is run at INCEP as well. Very useful in the 1 to 1.5 day time scale. You can see a couple of the parameters that we can look at it here, looking at precipitable water on the left, and a example of what the computer thinks the radar is going to look like on the right. Now, another really helpful convective allowing model suite that we use is called the HREF, and this is the main ensemble. So Joe talked about ensembles, basically a combination of different models. So we can an ensemble can either be the same model that has been tweaked with its initial conditions, several different times and put into an ensemble, or it can be a combination of several similar models. And so if you go to the next page, you can see the HREF is actually consists of 5 different convection allowing models that are all run together. And so each of these different models has different parameters and initializations that it helps it to resolve what it thinks is going to happen. It also includes the previous run of each model, so that we're not having these big swings that maybe some of the models want to do. It kind of gives a little bit of continuity. These are forecast really these were created to forecast very small scale features and in the 24-hour to 36-hour range. So when we're getting into if we got a snowstorm approaching and we're getting into the 24-hour time scale, we really would hope that we would have a pretty good idea on what we're expecting. And I'm going to show you some of the products that the HREF offers and how useful they can be. On this next page, you can see, first of all, this is an example of what's known as the ensemble mean, or we can see the Ensemble Max Snowfall. So this is just a depiction. I think this is the mean that I'm showing here. This is taking all the ensemble models into account. This is kind of the average value that the models think is going to happen. So this is basically the best guess at what we think is most likely. Now, say it could also show us the max snowfall, which would mean if everything went right, if everything fell into place, what's the maximum that we could expect? So that allows us to kind of get an idea of the level of uncertainty. If the max is pretty close to the mean, then there's probably a little bit more certainty. Whereas if there's a huge gap, then there's probably a lot more uncertainty in what's going to happen. Next. The next one is we can actually see all these different models plotted out separately. We can plot it that way so we can see, okay, which of these models specifically is showing, if one of them is showing 10 inches while the other 4 are showing 3 inches, then we know, okay, we can probably have a better chance of thinking we can throw one of those out because it's an outlier. So we can see them all separately if we want to as well. Next. It also, one of the really great aspects of ensembles like the HREF is probabilities. And so, for instance, this is the probability of the snowfall reaching, let's see, what is this? A 1 inch or greater. And so you can see that the scale at the bottom, we have a big area of 90 to 100% chance of 1 inch or snowfall, of 1 inch or more snowfall on the East Coast, really in the South Shore area. So this gives us high confidence that especially East Central and Eastern Massachusetts is going to see some measurable snowfall. Probabilities are a big confidence booster, or they can limit our confidence depending on what they show. And then another example of a probability that the HREF helps us look at is snowfall rate. So we can see, okay, how likely is it that we will see snowfalls falling? This is showing at 2 inches of an hour or greater. So this really highlights, even if you're not looking at the specific exact, county lines where it's delineating, because it's not going to be exactly right, it still gives you an idea, okay, this swath, this area has the best chance of the heaviest snowfall with this storm. So probabilities are very useful. All right, so what do we do with all these models all this model data we talked about? Basically, the main thing we're doing is we're taking all this in, we're comparing model to model, run to run, trying to figure out which of these models has the best handle of the atmosphere, comparing the models to what is happening right now, looking at satellite and radar, seeing which of these is initializing with what's actually happening right now the closest. If it looks very similar to what's happening now, we have better confidence in it. If it looks nothing like it, then we can probably throw that model out. As Joe talked about, as we get farther and farther away in time from a storm, the confidence is very much decreased. I like to think of it as kind of like a wagging tail on a dog. So if, say, you're at the tip of the tail, you're 10 days out, models are going to be flip-flopping back and forth, wagging back and forth a lot. As you get closer and closer to the dog, closer and closer to the storm event, that the movement's going to be much less back and forth. And as you get closer and closer, it's eventually converging on one answer. And that's what actually happens. And the closer we get to the storm, the closer the models are probably going to be. So we have to be able to apply known model biases that we, as forecasters, forecasting for however many years or winters before this, we've learned, okay, maybe the GFS, it has a dry bias. It usually under forecast precipitation, something like that. We take that and then we can apply it to future storms. Also monitoring trends, like I mentioned in the timing, is with each successive run of the model, is the storm moving faster and faster, slower and slower, something like that. And I already mentioned about how it's initializing with the current conditions. So all that stuff is called model interrogation. Now, the other main data that we look at with regard to models is known as model forecast soundings. And if you've taken our webinars before, you know what soundings are. They're basically vertical profiles of the atmosphere. And so the green line represents the dew point, the red line is the temperature, and you go up in the atmosphere. Going up in the atmosphere means you're going up on this chart. So the closer together the lines are, the more moisture. When they're right together, you know that the atmosphere is saturated. That's usually where there's clouds and precipitation. So looking at model soundings give us an idea of the profile of the atmosphere, and it fills in the gaps between where we actually take physical soundings using weather balloons. Here we do it on Cape Cod. There's one that's in Albany, many different sites around us, but in between those sites, we can use model soundings. All right, so some of the pitfalls of winter forecasting just want to touch on. One is relying on ensembles and probabilities, especially in the long term. Like I said, the closer you get to, and like Joe mentioned too, model error increases exponentially with time. And so models can flip-flop a lot run to run. And like I said, you have to keep that in mind. Secondly, out to 3 and 4 days is really the maximum of when we're going to be able to even have an idea of what's going to happen. So one of the main causes of this is that this jet stream energy that is going to eventually bring our storm 3 and 4 days out is just now or hasn't even reached the west coast of the United States. So the only way we're sampling it is through satellite. We're not getting any radar data. We're not getting any upper air soundings, weather balloon soundings from it, not any surface observations, that kind of thing. So there's a lot less data going into the models. And so there's a lot less info on what is going to happen in the future. Finally, another pitfall is relying on modeled snow accumulation maps. The main reason, one of the biggest reasons, is what's known as the snow to liquid ratio. Basically, for how much water falls, how much is that going to translate into in snowfall? Average is about 10 to 1, 10 inches of snow for every 1 inch of liquid. That's average, but it all depends on how cold or warm the temperature profile is, and we'll talk about that next. So yeah, huge grain of salt with snow accumulation maps from models, but they can generally be useful to just show you a general, okay, this is where the heaviest snow is probably going to be, lighter snow along the coast, that kind of thing. All right, so in our last Winter 101 talk, we talked about the necessary ingredients for winter weather. So I'll go through this pretty quick, but you need cold air, obviously, needs to be below freezing. You need lift or vertical motion in the atmosphere, something to cause the clouds to form and the precipitation to precipitate. And then you're going to need that moisture itself in the air, because if the air is lifting and if it's cold, it doesn't matter. If it's really dry, you're not going to squeeze out any rain or snow, as it were. Okay, so as meteorologists, what are we looking for when we're trying to forecast a winter storm? The first thing I'll talk about is the moisture. The main thing we're looking at, a couple of things like precipitable water, but especially what's known as relative humidity. Basically, we're seeing, is the air saturated? And it's not really just, is the air saturated, but it's, where is the air saturated? Is it saturated in the right layers of the atmosphere? So the focus is on what's known as the dendritic growth zone, basically dendritic flakes. This is where you're going to get the formation of the best, when you think of an ideal snowflake that accumulates really tall and really well. That's what we're looking for. This zone between -12 degrees and -18 degrees Celsius is where our snow growth is maximized. It's known as the DGZ, what we call it sometimes. Now, one caveat with our location here along the coast is because of our proximity to the ocean. If we say sometimes we have ocean effect snow coming off the ocean, the presence of salt nuclei in the atmosphere it's complicated, but it can basically lower that zone down to as low as -6 to -10 degrees Celsius. So a little bit of caveat right along the coast, but generally -12 to -18 is where snow growth is maximized. So we can look at that on a map. So this is an example of a model showing relative humidity within the dendritic growth zone. And you can see the blue is, I believe, 90 to 100% saturation. So this is where the best moisture is, comparing the NAM to the GFS. So we're comparing those two models. You can also look at it on a model sounding. So this is showing the sounding. The blue highlights the ideal snow growth region. And you see we have those lines are basically touching. So we have saturation within the dendritic growth zone. So that's good. Now, this also leads us to a few other things that we need, which is the lift and the temperature. So we'll move on to a temperature next, I think. So big question, is the air below freezing? And where is it below freezing? Is it in the whole column or just at the surface? People might think, oh, it's 20 degrees at the surface, it's definitely going to snow. But not necessarily. Again, we're looking at the dendritic growth zone especially, and then what the temperature profile does from there down to the ground. So we can look at that again on a map. We could plot it on a map. This is one of my procedures that I'll look at, and this is basically this is all from the NAM model, but this is the temperature at six different levels in the atmosphere, starting from the top left, the highest in the atmosphere, all the way down to the bottom left. And so you can see this basically can let me know, okay, it's freezing above 500 millibars, but just speaking in general, let's say it's above freezing 850 millibars and below. So basically the lower half of the atmosphere is warm. So I think, okay, maybe we might have snowflakes at the top. They're going to melt into rain before they reach the surface. So that's one way we can look at temperature. Another way is, again, looking at those really helpful soundings. So just looking, you see the 0 degree line, that's the freezing line. It's tilted on this map, but you can see that the temperature profile is what's known as isothermal, from where we see the words max lift all the way down to the surface. It's really hugging that freezing line right there. So it's just barely below freezing, if that. So it's going to be pretty marginal whether or not, some of that might make it to the ground or not. Right now, it looks like it will. But if there's even a little bit of an intrusion above freezing on the way down, then it might melt. So then I'll end on just this little the graphics showing this in another way. So this is the temperature profile, the atmosphere or the environmental temperature shown in blue with height. And so you see in this instance, we have all snow because from all the way from 3 kilometers, which is the base of the cloud, down to the surface, the temperature remains below 0 degrees Celsius. So there's not going to be any melting. That's easy. The next more complicated outcome is we have a warm layer right about 2 kilometers, and it's shallow. It's shallow enough that the snow only partially melts, and then it drops below freezing again before it gets to the surface. So then it freezes back into these little ice pellets or ice balls, and that's known as sleet. And then we can further complicate it with an even deeper warm layer and a very shallow cold layer. What that's going to do is that's going to melt those, it's going to be deep enough, the warm layer is deep enough to melt that snow into droplets. And then those rain droplets can become super cooled in the shallow cold layer. They might not have time to actually freeze into a little pellet, but they're super cold. So as soon as they touch the below freezing surface, they freeze on contact. And that's what's known as freezing rain. All right, so with that, I will pass it on to Rodney to do our last section.
thank you very much, Bryce. So one of the popular methods used by forecasters to forecast the precipitation type is what we call the top-down method. And as the name suggests, it's we look at the atmosphere from the top to the bottom at the surface. So, there are three questions that we like to ask ourselves, and that has proven to be pretty reliable over the years. So the first question is there snow or ice in the upper reaches of the clouds? Because if you don't have, you can have, ideal temperature profile, from the mid-level of the atmosphere to the surface, but if you don't have ice crystals, you don't get the initiation to form the snowflakes. The second question is, as the snowflakes fall, and that's assuming there's ice in the upper reaches of the atmosphere, is there a warm layer to melt them? So that's why it's so important to look at the sounding, and we will go into further details how to look at those soundings, and last but not the least, what happens near the surface. And like Bryce mentioned, if there's if you have, sometimes you look outside, it's like drizzling, but then it's actually in the 20s, and that's when you have to be worried about freezing drizzle, and that's the worst type of precipitation. Okay, so going back to the first question, so is there ice in the upper reaches of the clouds? And really, one of the key indicators, what's the temperature at where you can form ice crystals or snow, and ideally you really want to see temperatures at -10 Celsius or below. So -10 Celsius is about, I believe, 14 degrees Fahrenheit, if my conversion is correct. So if it's just too warm, you don't get the initiation. But as Bryce mentioned, for those of you who live near the coast, especially Plymouth County and the Cape Cod and the islands, if you can form snowflakes even as warm as -6 to -10 Celsius because of the higher concentration of salt nuclei. But for those of us who live further inland, you really want to have at least -10 Celsius, but really ideally -12 to -18 Celsius, as we will talk, elaborate on further. The second question is, as the snowflakes fall, is there a warm layer to melt them? And generally, these numbers here on the left-hand side of the table, they are used as a guide. Sometimes if the warm nose is, so it's not just about the temperature, how warm it is above freezing, but also how deep the warm layer is. Sometimes if you can have a warm layer of, let's say, 1 Celsius or 34 degree Fahrenheit. But if that layer is so shallow, it's not deep at all, you can still get snowflakes at the surface, but they will be kind of rimed snowflakes, so they're not as nice and doesn't accumulate as efficiently. But you can still get snowflakes even if the temperature profile is not quite all the way below 0 Celsius. But once you get into 1 to 3 Celsius, and especially above 3 Celsius, which is 37 degree Fahrenheit, you're going to melt the snowflake completely, and then that's when you get liquid. And if it is warm all the way to the surface, then you get rain. And number 3, what happens near the surface? You can have a deep, layer of sub-freezing temperature, but if it's above freezing at the surface, you get rain, unfortunately. And then sometimes you melt the snow completely through the atmospheric layer, but then sub-freezing surface, you get freezing rain. So number 3, we look at that's the other thing. We look at the model data, and lift is so important. And one of the key questions you have to ask yourself when you interrogate model data, I know a lot of you, since you signed up for Winter 202, I assume you would have at least some interest in winter weather. Even meteorologists and my colleagues, some of us love snow, and obviously we want to see the models showing a lot of snow, but then you want to ask yourself, does the meteorology support what the model is telling me? you can have 37 inches of snow in Fitchburg, but it's like, does the meteorology support that? And that would be a red flag. I mean, if you're not convinced by the model output. So one key ingredient is the lift. So you want to see, good upward vertical motion, rising motion of the air particles, because that's that way you can get the storm to form. And there are different ways to identify lift. So the first way is front. So there's frontal lifting, and sometimes if you can, you might have heard this term called front end thumb, and that's usually associated with a warm front lifting north, and kind of, ideally you would have a high pressure to the north, and you have a warm front kind of chipping away at the cold air in place, and that's when you get the front end thumb before it changes over or mixes with rain. And then you also get convergence on frontal boundaries. Sometimes you can get a coastal front, and our friends in Plymouth County and the Cape can attest to that plays a big role. So the other thing is omega, and basically it can be loosely defined as the spin in the atmosphere. A negative value represents upward rising motion of air, and ideally you want to see about 20 units of omega, so that minus 20 units. The other thing is frontal genesis, and that refers to an increase in horizontal thermal gradient. Ideally you want to see a good bit of frontal genesis, kind of around like 700 millibar to 850 millibar, that's around 5,000 feet above the surface. And also the last but not least, you want to see ideally high lapse rates, not necessarily at the lowest level of the atmosphere, but maybe between like 2 to 6 kilometers. That's about, kind of between 3,000 to 10,000 feet. So, but overall, for the best snowfall, you want the lift to be ideally within the dendritic growth zone. And tracking lift on the map, and these are some of our procedures. And Bryce and Joe have very good procedures that I sometimes steal from. And you can, on the upper left corner, you see that's the cold front, and sometimes you pull up a surface map, and it's pretty obvious where the fronts are based on the wind direction and the dew point spread across a small area. And then on the upper right corner, you see the 700 millibar winds, and this image is taken from the College of DuPage website. And what you want to see here is you want to see a speed convergence, and what that means is that, so on a highway, sometimes if you tend to drive slower, you see sometimes people will be tailgating you behind because they're driving faster, and if you're not careful, you can cause a crash. That basically is kind of like crash or accident in the atmosphere. So if you kind of have much faster air particles, crashing into slower moving particles, you get an area of lift. And remember, lift is omega, and that you get the upward rising motion of air, and that's when you get the storms to form. And the bottom images, that's frontal genesis and omega, and the brighter colors represent more favorable values. And one caveat is that you don't really want to focus too much on the exact location where the best lift is, because who knows, it might be 20 miles displaced to the east or west. And but it does give you, as a forecaster, it kind of gives you a ballpark, and it highlights to you the potential of, maybe you want to think about heavy snowfall rates, maybe 1 to 2 inches per hour if possible, at some, somewhere in southern New England. And this is looking at the sounding. Basically, it gives you a snapshot of vertical profile of the atmosphere. And on the left, it shows that's the omega. Clearly, the longer it is, the higher the omega. And in this case, it coincides with the dendritic growth zone. In this case, minus 12 to minus 18 Celsius. So you have good saturation in this part of the atmosphere, and you have good lift. You have a pretty good chance of forming some snow. And this is a cross section of the same sounding that we showed you in the previous slide. But you can see here. So the dendritic growth zone is depicted in the pink zone, and that's strictly -12 to -18 Celsius. Again, for those of you who live in near the coast, that DGZ may be as low as -6 to -10 Celsius. So, you know, in this case, you will want to focus on the omega, where the omega is in that. In this case, it's highlighted in red. That's the negative values, and you know, ideally you want to see -10, better still -20 units of omega. And if you can get the omega to coincide with the DGZ, a good chance you can get a good snowfall rate. And these are some of the other meso analysis that we look at. And you know, sometimes we look at so many resources, and something might be overwhelming. But you know, I mean, nowadays there's just so many things, good things to look at, and to ensure the forecast is as accurate as possible. And these are more things we look at, and just one quick thing I want to highlight. So the left image, that's the upper level divergence, and that's roughly about 250 millibar, 500 millibar in the atmosphere, and 500 millibars kind of halfway between the surface and the top of the atmosphere. That's around 18,000 feet, and at that level, you want to see what we call divergence, and that's the opposite of convergence. If you think about it, going back to the highway accident analogy, at the surface, if you can have air particles to crash into each other, you know, you will force them to lift up, and then at the top of the atmosphere, if you think about it, it's kind of like a ceiling or a lid, and so the air particles will hit the ceiling and then they will diverge. So if you see good signature of upper level divergence, that means that you have lower level convergence at the surface, and that kind of you know, if you think about it, it's a conveyor belt, and that supports upward rising motion of air. So you know, we've talked so much about model data. You know, as a storm gets closer and closer, we want to look at observations to see if the models are initializing correctly. And one key resource that we look at is satellite data. And you know, satellite data is just becoming so advanced nowadays, and it's almost like looking at radar. You know, it's like especially if you have you may have heard of the 1 minute interval satellite imagery, and that's you know, in this case you're looking at the visible satellite, and you can see the day transitioning into night. So it's, you know, as nighttime approaches, you lose the sunlight, and you know, you don't get visible data anymore, but there are different types of satellite data that you can look at. And I talked about radar, and one of the key products that we look at is called the correlation coefficient, and that's basically how different or how similar the hydrometeors are. And hydrometeors are, you know, your raindrops, your sleet, snowflakes, and no snowflakes are created equal. So you know, the correlation coefficient is a ratio, so between 0 to 1. So 1 being, you know, homogeneous hydrometeor. So if you have a rain event, chances are your correlation coefficient will be very close to 1. Or if you have a straight out snow event, then, you know, you may be talking about 0.95. But if you start to see correlation coefficient below 0.9, that's when, you know, you see, okay, maybe it's not just snowflakes that are flying through the air, you know. And I think in the next slide we will talk about the bright banding, but you know, so basically you have the radar dome. In this case, it's located right next to our office in Taunton, and it shines a kind of a beam through the atmosphere, and it dissects what is falling through the atmosphere. And in this case, clearly, if you have mixed rain and snow, your correlation coefficient is going to be reduced, indicating rain mixing in with the snowflakes. And yeah, this is what I call the bright bending signature. You can see kind of like a bright ring around the radar, and this is in a mixed precipitation event. That's roughly speaking, your melting layer, and sometimes it's very accurate. Based on the reports, the amping reports that we receive, people kind of located underneath the bright bending are observing mixed precipitation. So it's a very, very skillful product here. And yeah, here it is a loop showing one of the winter weather events that we experience. You can see that the warmer air trying to lift north, and you can see, sure enough, that bright bending is also lifting north as well. And on the right hand side, you can see sometimes the rain snow line would waver as well. So if you're kind of people in that zone, would have to you really monitor the weather, because you could get all kinds of precipitation types in a short period of time. So to the west of the bright bending, there's snow. To the right hand side, that's rain. We talk so much about model sounding, but do you also know that you can get real time sounding as well? And on the right hand side, that's actually Bryce releasing the weather balloon now, I believe when he was in Spokane, Washington. And typically that's done at least twice a day. In high-end weather events, it might be done as many times as 4 times a day. If you think about the hurricane, so basically every office in the country would pitch in to help out with the efforts, and but generally twice a day. And for us, we do it over in Chatham on the Cape. So next time if you go to Chatham, you might be able to see our upper air site. And on the right hand side, that's actually an observed sounding. So that's actually real-time data. And in this case, what you can see, the green line is the dew point temperature. You can see there's a mid-level dry air layer, because the dew point is way low. And this weather balloon, sometimes they get up to over 50,000 feet before they pop. And and when they pop, it's like they will fall back to Earth. But the thing is that since we release it in Chatham, and with the jet stream, it usually will land in the ocean, so we don't really get too many of our equipment back. But sometimes, if you keep your eyes open and peeled, you can get the equipment from other offices, and there would be on the package, you would say it's a harmless instrument, and encourage you to return it to the office of origin. And this is showing the real-time analysis, and again, really, quality observations are so important, and there are different ways to look for observations, and I'm not going to talk too much about that. And I think this is the last slide. So amping, great product, and it's really easy to use, and you don't even have to take snow or rain measurement. All you have to do is, if you look out the window, just tell us, report to us what precipitation type you are seeing. And this is really important in mixed precipitation events, because it really verifies help verify our forecast and fine tune it. And so with that, we just really thank you for your time. Before I pass it back to Joe, these are the websites that some of the things that we talk about. And but once again, thank you so much.
All right, Rodney, thanks, and Bryce, thank you. We're going to go ahead and we'll answer your questions. We'll do as many as we can here. If you want to hang around with us, we'll go a little past 8 o'clock. That's fine. Let's see. Question from Samuel: is it hard to forecast ice storms, and are we due for one? Well, guys, I would say that's probably the hardest thing we forecast.
Yeah, definitely.
Because a matter of a couple of degrees can make all the difference. So, usually your more severe ice storms occur with much colder temperatures in the 20s, as opposed to maybe right around freezing. But yeah, that's where we look for that deep, warm layer aloft, that warm nose that Bryce and Rodney talked about, and then temperatures below freezing at the surface. So, whether we're due for one, that's hard to say. We don't see them very
Yeah.
often. We may see a few light icing events each winter, but yeah, maybe this winter. I mean, it's been kind of on the milder side, so
Don't put that on us,
storm
Joe.
tracks. Yeah, we'll see what happens. I don't know. All right, from Chris, can you explain why for the big December 18th storm, even though it was pretty cold for the duration in the 20s, the snow was so heavy to move and shovel? I was surprised how hard the snowblower was working, and for the finish work, how hard I had to work to shovel it. Well, that goes to what Bryce said. It really depends. Your lift, it's where your lift is centered and what the temperature is. So in that case, Chris, the lift was centered actually in some warmer air aloft. So we didn't have that great dendritic growth zone necessarily where it's colder and you get that nice powdery snow that really piles up. So even though it was in the 20s, aloft where the snowflakes were being produced, it was a little bit warmer. So we had kind of that heavier, wet snow consistency. So good question. And join us next week, Chris, for the review of that storm. We'll actually go through that a little bit. That's a good question. So from Sheldon, similar question, how is wet versus dry snow formed? Again, it has to do with where the maximum lift is occurring. So if it's occurring in the dendritic growth zone, that's typically a drier, powdery snow, or even if the lift is above that and colder, say minus 20 Celsius and colder air, it's going to be a lot more powdery, as opposed to if the lift is in warmer, relatively warmer air, maybe minus 2 to minus 4 Celsius. That's going to be your wet, heavier snow.
Yep.
Okay, from Ethan, what does it mean when reflectivity is between 0 to 20 dBz? Does that mean that precipitation is falling but evaporating? Well, Ethan, it sometimes means light precipitation or just clouds. Sometimes it's detecting the moisture in the clouds, but we can see things like drizzle or flurries sometimes, or just a very fine light snow or light rain from that. And he has a second part of the question, Bryce, and I think you know the answer to this one. What is that really bright area of reflectivity over central Rhode Island, which I've seen a lot right now?
Yes, is it the dump? There's
It's
a tile,
it's
a landfill.
Yeah.
A landfill.
There's
a
something
piece of land that's sticking up.
Yeah, there's something there that's highly reflective. So we actually have to kind of fake it out from the radar so it doesn't show up as rainfall. So
same thing happens with windmills sometimes
over
the ocean.
It's called ground clutter. So a lot of wind farms, turbines, sometimes even land features will show up as ground clutter, buildings in particular. It's just a piece of clutter. From Stephen, about sudden stratospheric warming. Science Daily had an article on that over Europe, leading to increased snow. Do we have that here? Ooh.
Oh gosh, that's
well, that's actually an area of new research for winter weather. So when there is what's called sudden stratospheric warming or sudden warming in the stratosphere, there's a correlation, and again, it's one of these teleconnection type things to increased jet stream activity. So over Europe, Stephen, I'm not positive if that's a direct correlation to North America. I think ours has to do more with Asia, if I remember. But that's a newer area that we really, when we're doing our forecasts, we're not really relying too much on that because it's more of a thing that lasts over weeks as opposed to days. That's more in the realm of like the Climate Prediction Center. But there is some research that shows that sudden warming in the stratosphere can lead to a more active jet stream. And so I believe that if it's over Asia, Northern Asia, that's more conducive for activity here in North America. I could be wrong on that, but I think that's what it is. From Benjamin, are we behind snowfall? Are we behind in snowfall for this season? Bryce or Rodney? You guys know offhand?
Not offhand, but while we're looking at another question, I can look where we're at.
Okay, you'll look at that.
And
from Benjamin, why is it called the benchmark? That's just because it's kind of the benchmark for coastal storms and their effects on our area. So it's that 40 degrees north, 70 degrees west. That's kind of the standard for where the storm's going to track and what the effects will be. Let's see. And John had a question on sudden stratospheric warming. Can it be forecast? Yes, but John, that's at longer time ranges. So I would check, actually, if you're interested in that, and for Stephen too, check out the Climate Prediction Center website. I think there's more information there, or you can do an online search. Let's see. From Kevin.
All right. So with the
go ahead, Bryce.
the question about where we're at with snowfall for Boston, right now we're above the at least for the meteorological winter, which is December, January, February. We are at 13.2 and normal is 11.9. So
okay. So close to average, maybe a little bit above. Yeah.
A little bit above, but
okay. Well, we'll see how the rest of the winter turns out. I guess dry for the next few days.
Yeah, about to say we'll probably fall below in the next week.
Yeah. All right, let's see from Kevin. Do surface observations tell how cold the temperature profile is aloft and whether it will produce snow? No, that's actually completely independent, Kevin. So again, it can be, you can have snow when it's 35, 36 degrees and it's colder aloft. You can have rain when or freezing rain if it's 26 degrees at the surface. So that's why we need to look at the whole profile of temperature going from the surface aloft. So good question. From Kevin, let's say there's a snow event likely within 36 hours. Which tools would you look at and in what order? Well, I'm going to hand that to Bryce and Rodney for both of their answers. What would you guys look at if we got snow within 36 hours?
Yeah, so definitely when we're talking 36 hours, as far as model data, the href is coming into play. 36 to 24-hour range, because like I mentioned, that has the highest resolution models, and it's an ensemble product, so it takes into account multiple solutions. So the href is one of our biggest tools, and at that point where it's close enough that these features are already being tracked over North America, most likely on satellite. So one of the best things we can do to kind of figure out which of these models we should follow more closely is comparing how it's initializing. So I would say look at the NAM 3K and look at the 500 millbar heights, which basically I just want to compare that to what I'm seeing on satellite. The trough, looking at the troughs and the ridges. Does the trough line up? Is it digging deeper in satellite than the NAM showed that it was going to? If it is, then I know that it's off. If it's really close, then I can say, okay, at least it's handling this feature well right now, so I can put a little more trust into what it does in 24 to 36 hours over us. Get an idea of that. So, and also at that point, we're getting sounding. So, we want to know is the antecedent condition, so that the atmosphere over in southern New England leading up to the storm, is it cold or is it warm? So we're looking at soundings from Chatham and Albany to see how deep the cold air is, if we have cold air at the surface and aloft. So we're looking at what the atmosphere is going to be primed with before the system even gets here. So I'd say soundings, the href, and satellite are some of the biggest things I use. And I don't know if Rodney had his headphones on. Rodney, did you hear the question? He was getting briefed by Bill, so.
Oh, it's okay. Well, that's plenty. And yeah, and for me, I would kind of do the same thing, Bryce. Sometimes we still have uncertainty, even 24 to 36 hours with some of the details.
Oh, yeah.
I'm starting, pretty much with those global models. Make sure they have a decent handle, and then working my way down to kind of get into the details. So I'll go from like the GFS or European or UK Met to Canadian, down to the level of the NAM, that 12-kilometer model, and then, like Bryce said, the higher res. To really define those snow bands or, rain snow lines, those sort of things. So you just kind of work your way down in scale. Question from Mike. Can models self-learn from past errors? No, they don't, but what's happened is verification is done. We have a whole center of folks down in DC, and that leads to improvements or upgrades to the model. So again, they're just a series of equations. So what happens is the model is kind of tweaked. Maybe one parameter is changed a little bit to better handle a situation. We know, for example, let's take the GFS, the current version. We know has a bit of a bias where if there's a low coming off the Carolinas or the Southeast, it typically tends to be too far suppressed from New England, especially when it's the southern part of the jet stream. Whereas there's an upgrade to the GFS, which actually is scheduled to come out in February, and that handles it a lot better. So it's kind of losing that bias of being too dry and too far offshore. And that was the case with that December 16th to 17th storm that ended up giving us a lot of snow. If people remember, the days leading up, the GFS showed almost nothing here. It was offshore and then began to trend north. Well, the version that's going to be implemented in next month actually did a much better job a few days out. So that's one example of how the models are improved. They can't necessarily learn, but the model developers can take that information and work on improvements. From Kevin, and I'll hand this one to Rodney since he's our global guy. Does the polar vortex wiggle or bend at its position in the polar regions, and how does that affect cold spells in New England?
Yeah, thank you so much for the question. That's that's really a, like Joe says, a really global question. You know, right now, you know, we have, you know, some of you may be wondering, we have a deeply negative NAO, but why is it that we are not getting the snowstorms? And that's because of the placement of the NAO. It's not quite in the right place, and that basically results in Pacific air being flooded across much of the conus. And then, in fact, the displacement of the polar vortex actually right now is actually causing a cold wave in much of Asia. If you take a look at some of the temperatures, you know, much of East Asia, you know, China, Japan are well below freezing right now, and that's because of the displacement of the polar vortex. But there are some indications that you know, maybe later this month the displacement can be such that it actually results in a cold outbreak over the eastern half of the country. No guarantees, but the signs are, you know, there are some clues pointing to that happening. But you know, it's given that it's still two weeks, maybe 3 weeks away. Just have to take it with a grain of salt, and we'll see how the models trend in the upcoming days. But yeah, I mean, going back to the question, it is hard to say exactly how, you know, the kinks in the polar jet stream will work out to bring the cold air down which way, but typically we do know enough to know, okay, is the cold wave going to be over Asia or is it going to be over North America? But in this case, right now, we have to be patient.
Right, and Rodney, also, I mean, climatologically, or what we normally would expect, our coldest temperatures of the year are really like the latter part of January into early February. So we're not even there yet. It's still a bit early for us to really get into the true cold air. So Kevin, be patient. We'll see what happens in the next few weeks. From William, is it difficult to forecast sleet? And I would say along the lines of freezing rain, yes. It has to do with the depth and the warmth of that mid-level warm nose that we talked about. So sleet and freezing rain are definitely when we get the trickiest parts of our forecast. Rodney and Bryce, I think you would agree with that too.
Yes, if it could just be snow or just rain, I would love it. It would be so easy. But yeah, the sleet, freezing rain, that's the hard part.
Yeah, what we like in the wintertime are the slam dunk blizzards where it's all snow everywhere and, you know, no problem. So,
Exactly.
Jonathan, our friend, says, thanks, guys. Have a great new year. Jonathan, you too. Thanks for joining us.
Thank you.
From Peter, since soundings are taken relatively far apart, are there often significant differences in values like temperature, humidity, for points in between? Bryce, I'll hand that one to you.
Yeah, I mean, there certainly are, and it obviously depends on the weather pattern. If you've got one sounding site that's right beneath a deep trough, and then one that's further east underneath a jet that's dry, a ridge that's drier, you know, you can get very significant values. I mean, between Cape Cod and Albany, there can be a real big difference, especially say you're getting a dry slot coming in, but it hasn't reached all the way to Cape Cod yet, but it is over eastern New York. That profile is going to be drastically different, even over that relatively short distance. But they are, like you said, they're spaced apart so far that that's why we need the model soundings to fill in the gaps, because there could be quite a bit of difference between each, from site to site.
All right. And just a couple more questions here. One from Scott about the model self-learning. Is anyone working on a machine learning, artificial intelligence-based model? And actually, Scott, yes, not a particular model, but actually a way to incorporate machine learning into essentially the fire hose of data that we have. So there's actually plans in, say, the next, I would say, 5 years to really incorporate machine learning into the model output. So I think you'll be seeing a little bit more of that in the coming years, because as you see, there's so much data for us to look at, so many model fields to look at. It would help to have some sort of machine learning technique to have the machine do some of the thinking or the output for you and present it. So that's actually an area that's just starting to be explored. And I would think in the next 5 years, we'll be seeing a lot more of that. So people like Bryce and Rodney will have more fun than I will be having, but that's okay. And last one is from Ethan. How do the high resolution models handle very high snowfall rates? He remembers one of the recent nor'easters that apparently had high snowfall rates around 5 inches an hour, give or take 1 or 2 inches. And I guess I can finish with this one, guys. They tend to do a pretty good job, but it's very rare, I think, and you guys can agree or disagree. It's rare for them to really capture the extremes, like 5 inches an hour. You might see signals for like a 2 to 3 inch per hour, but typically you won't see more than that. And that's where we kind of add the value to that. So if like the HREF is showing a high probability of 2 inch per hour snowfall rates, maybe a lower probability of 3, we might look at some of the ingredients going in, like Rodney showed that the frontogenesis map, or the speed convergence in particular. With that December storm, we were actually looking at that. That was tremendous speed convergence. You had winds from the south at over 80 miles per hour coming right into easterly winds at 10 miles per hour. That's like hitting a wall. But instead of hitting a wall, it forces the air to go up. So that's tremendous, tremendous lift. So I remember looking at that, we were saying, boy, the model is saying probably 2 inches an hour. We could see 3 to 4 inches per hour easily out of this. And some places did see that plus even more. So yeah, Ethan, you probably won't see the extremes, but if you see a signal for, 2 inches per hour, 3 inches per hour, that should, raise kind of a flag and get you to look at some of the data a little bit more closely, because you're probably going to see a little bit more than that. So great question. And just, I'll wrap up here by saying, this is kind of just an overview of winter weather forecasting techniques, but I would really encourage those of you, especially our aspiring meteorologists in the audience, to attend some of our event reviews, because we go through a lot of what we were thinking in our forecast process for the event. So in particular, the December 16th to 17th storm, and even the Christmas Eve to Christmas Day storm, kind of things that we were looking at to forecast different aspects of those storms. And it's by gaining that experience that helps you with a little bit of intuition, which is something all forecasters need. It's that working these events. Bryce and Rodney, you guys can probably say it as well. You've been here a while now. The more events you work, the more comfortable you become, and the more things you pick up from subsequent events. So, to our aspiring meteorologists or weather hobbyists out there, join us for the event reviews or check them out on YouTube, because those will really help teach these concepts as well. So, Bryce, Rodney, I'll leave the last words to you.
Well, I would just say thank you for joining us, and I really enjoyed. We really enjoyed putting this together and kind of getting to explain a lot of it. And again, any more questions, please email Joe, and we'd be happy to answer. And more, if we couldn't get into it tonight, answer those questions that you may have. And I'll plug my Skywarn training coming up in the spring. If you want to learn about a little bit more about severe weather, we're going to follow that Skywarn training up with a weather forecasting, or Weather 202, which is just going to be a little bit more about severe weather forecasting later in the spring. So if you like this, you might like that one as well.
And of course, please send us your feedback. My email address is there, and you have it on your webinar confirmation. If you've got any ideas for future topics, send them our way. We're already working on a few that we've had suggestions from all of you. So we really appreciate everybody attending. And we will see you, I guess, in a week from tonight to talk about December 16th to 17th.